Have you ever stopped to think about what you're actually made of? Or your phone? Or the stars way out in space? It sounds like an impossibly huge question, right? But the answer, you'll see, is actually pretty simple. Everything, and I mean everything, is built from the same basic set of ingredients.
It's one of those questions that really gets to the heart of, well, reality. And what's so cool is that despite all the different kinds of stuff out there in the universe, it all comes back to a surprisingly small set of tiny, fundamental building blocks.
And the answer is the atom. This is it, the smallest possible piece of any substance. The easiest way to think about it, atoms are like the Lego bricks of the universe. Every single thing you can see and touch, from a gigantic mountain to the smallest germ, is just a different, really cool arrangement of these basic bricks.
Now, unlike a simple Lego set that might just have one type of brick, nature has this whole amazing collection of them. And each one has its own unique character, its own special properties. We call these different types of atomic bricks the elements.
So what that means is that an element is a substance made up of only one kind of atom. If you have a bar of pure gold, it's not a mixture of things. It is a massive, jam-packed collection of nothing but gold atoms. The same is true for a chunk of iron. It's just a huge pile of iron atoms, and that's it.
And to keep track of all these different bricks, scientists came up with a handy shorthand. Each element gets its own name and a unique 1- or 2-letter symbol. It's just a simple way to label them, so H is always hydrogen, and Au, believe it or not, is always gold.
And just like you can sort Lego bricks by their shape and color, elements can be sorted into these big families. The two biggest are the metals and the nonmetals, and you can see they have totally different personalities. Metals are usually shiny, strong, and great at conducting heat and electricity. Nonmetals, yeah, they're pretty much the opposite. And these properties are what determine how we can use these bricks to build stuff.
Okay, so we've got these elemental bricks, but what are the bricks themselves made of? I mean, if we could zoom in way, way down, past the surface of the atom itself, what would we actually find in there? Well, let's take a look.
This is amazing. Every single atom in the entire universe is built from just 3 even smaller subatomic particles: protons, neutrons, and electrons. That's it. All the incredible variety of all the elements we see just comes down to different combinations of these 3 little things. What's really fascinating, though, is how they're all arranged. As this chart shows, you've got the positive protons and the neutral neutrons packed together in this dense little core called the nucleus. And then, whizzing around that nucleus in this kind of blurry cloud, you have the tiny negatively charged electrons.
So what makes one element different from another? This is the key. It's the number of protons. That's the whole secret. An atom that has 6 protons is always carbon. If you could add just 2 more to make 8 protons, it is always oxygen. This number, the atomic number, is like an unchangeable ID card for every single element.
But atoms don't just sit around in isolation. No way. They interact, they bond, they build all kinds of complex things. And the way they do this is by trading their outermost particles, those little electrons. This electron swapping is basically the foundation of, well, all of chemistry.
Remember those element families we talked about? Well, they have very different personalities. The metal bricks, for instance, they tend to be pretty generous. They actually like to give away 1 or more of their electrons to other atoms. It's just an easier way for them to get into a nice, stable state. So, think about it. When a neutral atom loses a negative charge, like an electron, that perfect balance gets thrown off. All of a sudden, the number of positive protons in the center is greater than the number of negative electrons whizzing around. This imbalance gives the whole atom a positive charge, and we have a new name for it, a positively charged ion.
Let's look at a real example: sodium. A normal sodium atom has 11 positive protons and 11 negative electrons. Perfectly balanced, 0 charge. But it's a metal, so it really likes to lose 1 electron. Now, it still has 11 protons, but it only has 10 electrons. That leaves it with a net charge of +1.
And then you've got the nonmetals, which have the complete opposite personality. Instead of giving away electrons, their whole tendency is to attract and grab extra electrons from other atoms to get to that same stable state. They're the takers.
So, as you can probably guess, when a neutral atom gains an extra negative electron, the balance tips the other way. Now, the negative charge from all the electrons is stronger than the positive charge of the protons.
The result? An atom with an overall negative charge, which we call a negatively charged ion. And a perfect example of this is chlorine. It starts out with 17 protons and 17 electrons, but it loves to gain one more electron. So now it has 18 electrons, but still only 17 protons. And the result is a chloride ion with a net charge of -1.
Okay, so we have over 100 different types of these elemental bricks, each with its own special number of protons and its own chemical personality. How on earth do scientists keep all of that straight? Well, they use a master blueprint.
And this is it, the periodic table. It might look a little scary at first, but it is, without a doubt, one of the most powerful and elegant organizational tools in all of science. Its genius is that it's so simple. It just arranges every single known element by its atomic number, one after the other.
But the true magic is in its structure. The table is set up so that elements in the same vertical column, we call that a group, all share similar chemical properties. They behave like a family. This means if you know how one element in a group acts, you can make a really good guess about how its neighbors will act too. It's like the ultimate cheat sheet for the entire universe.
All right, so that's a lot of theory about protons and electrons in tables. But why does any of this actually matter to you? It matters because these aren't just abstract ideas. These are the bricks that combine to build the entire world you live in, every single day.
I mean, just think about your day. The lithium that powers the battery in your phone, that's an element. The aluminum in the can of soda you drink, that's an element. The life-saving oxygen a patient breathes in a hospital, the chlorine that keeps a swimming pool safe, even the helium in a birthday balloon, these aren't just concepts, they're pure elements, each one just a different arrangement of those same fundamental building blocks.
It's a pretty wild thought, isn't it? The entire universe, with all of its mind-boggling complexity, is built from a limited set of elements, which themselves are made of just 3 tiny particles. It really leaves you with a final, pretty exciting question. Now that we know the recipe for the cosmos, what will we decide to build with it next?